All right, hopefully you've already checked your answers on the answer sheet. I am going to do part 1 in this video, so that's going to be numbers 1 through 18. What I'll do is I'll put over here in the top left corner what number problem we're on. So if you want to just scroll ahead in the video and look at that top corner to find the specific problem, go ahead and do that. I'm going to work out all of them because, who knows what problems you're going to need. So starting with number 1. In the year 2000, the world population was 6.08 billion and was increasing at a rate of 1.21% each year. Write a function for the world population. So our function that is given to us, or at least the format, it says on the paper, a of t equals a 1 plus or minus r to the t power. Now this is the exact same thing as y equals a 1 plus r to the x power, which is kind of what we did originally. A of t is just sort of like the amount after a certain period of time, which is the answer. It's the same as the y equals. So you don't really have to concern yourself with that too much. But we're going to write a function for number 1. So we're going to have y equals. Now this a value, the lowercase a value, is representing our starting amount. So we're talking about, starting in the year 2000, the world's population was 6.08 billion. So I'm just going to leave it as 6.08 and just know that basically it's still, and I'm still referring to billions here. And then we're going to have 1 plus or minus r. Now, plus will be for growth, minus will be for decay. And it says in the problem that the population was increasing. So we're going to have 1 plus r. Now, our rate is our 1.21%. Now, 1.21, yes, it's a decimal, but it is still a percentage value. So when you have a percentage value, you have to remember to move this decimal place 2 places left. Now, of course, we skipped an empty space, so we're going to fill that space with 0. So the decimal we're going to fill in here is 0.0121. And then to the x power, or you can say t power, it's the same thing. I'm going to just leave it as x. But that's your equation for number 1. For number 1b, I guess it's asking whether it's growth or decay. We've already mentioned that it's going to be growth. And now to do part C, I'm going to have to close this real quick and open up my calculator. So in part C, here's how you would do it. You can go to your y equals and you can type in the equation you just came up with. So we're going to put the 6.08. Remember, that's still in billions, keep in mind. So, but we can leave it like that just as long as we remember that's billions. 1 plus 0.0121, close parentheses, and then to the x power. Now that's important that you put the x in there, because if you don't put the x in there, then the table we're going to look at is useless. So equations typed in. Now we're going to go to the table. If we hit second graph, it'll take us to the table. So what the table tells us is after how many years what the population is. So at 0 years, which is the starting amount, we had the 6.08, which we know. After 1 year, it's 6.15 billion. After 2 years, it's 6.2 billion, right? And so on. Now, part C is asking, predict the population in 2020. Now, we're starting at the year 2000, which means 0 on my table is the year 2000. So 1 is the year 2001, 2 is the year 2002, and so on. So I'm just going to scroll down until I get to, obviously, 20, because 20 will be the year 2020. And that will tell me what my population is in 2020. So it's 7.73 billion, remember. So that's the answer for C there. Number 2 is kind of the same thing. So for number 2, we are going to make an equation. Again, we're going to put it in the y equals a 1 plus or minus r to the x power version. So y equals a. A is our starting amount. Now, the value of our computer that it says in the problem is starting at $3,000. So that's what I'm going to use for a. And it's decreasing. So if it's decreasing, we're going to subtract instead of add. It'll be 1 minus r. Our rate is 30%. Now, as far as 30 goes, the decimal point would be right here after the 0, right? Because that's 30. You move the decimal place 2 times left, it's going to end up there, which makes it 0.30. I'm just going to leave it as 0.3, but you can write it as 0.30 if you want to the x power. So there's your function. We've already mentioned its decay. We know it's decay because it says the value is decreasing. And you can do the same thing in the calculator to find out what the value is after 4 years. So go back to our calculator and we'll go to our y equals. We'll clear this and we'll type in this equation. So we have the 3,000, 1 minus 0.3 to the x power. And then we're going to go second graph and take us to the table. Now, we're looking after 4 years. So we're just going to go up here. We're going to look at 4 years, and it's 720.3. So $720.30. We could probably say $720, but we're going to go ahead and say $720.30. All right, so now moving on to number 3. So number 3, rewrite each exponential equation in log form. So we're going to have to remember this property. The property that we have a log, I'll call it with a base b of a equal to x. The exponential version of this would be b to the x power equals a. So an example, we can have log base 3 of, let's say, 27. Well, no, let's not use 27. Let's use 81 equals 4, which is a true statement. The exponential version of this would be 3, which is this number, raised to this power, the 4th power, to equal the main component of this log, which was 81. So 3 to the 4th power equals 81. So the little index number is going to be the base for our exponent. The x, or whatever's over here, whatever this equals, is the exponent. And then the main part of the log will be on the other side of the equal sign. So it's just a matter of rearranging. So we have 6 to the x power equals 216. So we're going from exponential form to log form. So if you remember the transition, I'll go ahead and put it back over here. So this is kind of the property I'm basing it off. So I already have an exponential form. So b, which is 6 in this case, will be the little part of my log. It'll be log with a base of 6. Now a of my log comes from what we equaled. So it equals 216, so that's going to be the main part of my log. And then equals x. X was the exponent, so my exponent here is x as well. So that's the log version for number 3. Number 4, we have x to the 2.5 power equals 32. Again, if we're using this property, gonna try and figure this out. So the b, which is the base of the exponent, is x in this case. So we're gonna have a log, and that's gonna be the base of the log. So a log with a base x. A is going to be what our exponential equaled, which is 32. So it's going to be log base x 32 equals x. Now the x comes from the exponent, and our exponent was 2.5. So that's the log version of number 4. So basically, if you want to think of it like this, if you read this left to right, the first thing you're going to see is x. The second thing you're going to see is the 2.5. And the third thing you're going to see is a 32. When you put it in log form, if you read it left to right, of course you have log. That's kind of a given. But x, the first thing you see, the 32 is the second thing you see, and the 2.5 would be the third thing you see. So as far as the position goes from what you see first, second, or third, x or whatever here is first both times. So in terms of like positioning, this, whatever's first is first down here as well. So it's easy to remember where that goes. But what's second and third rotate, because what used to be second is now third, and what used to be third is now second. So these two things sort of flip-flops positions as far as what you see when you read it left to right. So that's kind of my way of remembering it. Number 5, just to do these kind of quickly, we have 6 to the 5th power equals 7,776. So log version of this, log, again, the first thing I see is 6. That's going to be the base. It's also going to be the first thing here. We're going to switch these spots. So that means the next thing I'm going to write is 7,776 equal to 5. There we go. I'm going to put parentheses on that just because it was kind of big there. Number 6, x to the 4th power equals 16. So we're going to have log. Remember, x is the first thing here. It'll be the first thing I see in the log. So log with a base x. We're going to switch these spots. So log base x of 16 equal to 4. Be how you write that. So again, it's just a matter of switching things around. Number 7. Number 7, we have the opposite effect. We have the logs, and we're going to write these in exponent form. Same idea goes. It's just the opposite of what we just did in the last 4 problems. We're going to, obviously, the first thing I see here is 5, so it's going to be the first thing I write when I write in exponent form. Now, 5 to what power? Well, remember, these things will switch. So 4 will be the exponent here, and this equals 625. So this is just the opposite process. If we look at the property that we're talking about here, we were going from exponential to log in the last 4 problems, but now we're going the other way. We're going from log to exponential. Same goes, though. Just remember that the first value is first value, and then the second and third sort of switch roles, and you should be okay. Number 8. Number 8, we have a log 2 x equal to 6. So exponential form, 2 will be the base of the exponent. The 6 will be the exponent. And then x will be what this equals. So 2 to the 6th power equals x. Number 9, log base 6 of 216 equals 3. So the first thing is 6. Second thing, it'll be to the 3rd power equals the 216. Again, just quickly rearranging these. Number 10, log base 3 of 243. I want to put parentheses on that. Equals x. Same idea. 3 is the first, so it'll be 3 to the x power equal to the 243. So remember, you're just keeping this first and then switching these two, and you've got your exponential equation. It's very important that you know how to do that, by the way. Number 11. So now I definitely need you guys to check these, because we're doing 2 things. We're going to combine these logs into one log. I'm going to put parentheses on them. I know it doesn't have the parentheses written on your paper, but it does make for a good visual. So I'm going to combine these into a single log. Now, these are both common logs, so they do have a base of 10 here. That's not really important for this problem, but I did kind of want to remind you that that base is still 10. So when we combine them, we still have a common log as well. So it's going to be a common log with that base of 10. But adding logarithms means we're going to take the values of these logarithms and multiply them. So instead of doing 2 plus 5, we're actually doing 2 times 5. 2 times 5 is 10. So there's my logarithm. Now, that's only part of the problem. We have log base 10, but it says evaluate. I want to know what this actually equals. So what number does this equal? Well, I'm going to call it, since I don't know what it is, I'm just going to call it x for now. And I'll show you how we can do this in our heads without the calculator. So I'm going to convert this logarithm into exponent form, just like I was doing a couple minutes ago, from 7 through 10. So to do that, remember that the base here is 10. It's kind of relevant now. The base there is 10, then this whole thing in exponent form would be 10, which is this number, the base, to the x power equal to that 10. So now I'm thinking, okay, 10 to what power equals 10? 10 to the 2nd power, 10 to the 3rd power? No, it's 10 to the 1st power. So that tells me that x must be 1. That log 10 is just simply equal to 1. Number 12, if that kind of went over your head, stay with me for number 12. We can try to do the same thing. So we have a log base 2 of 16 minus log base 2 of 2. So the log base 2 of 16, all right, now we're going to combine these into a single log. Now, since they're both logged with a base of 2, then my logarithm that I combine them into will also have a base 2. But when I'm subtracting, as I am here, I'm not going to subtract 16 minus 2. This minus sign means divide. So we're going to do 16 divided by 2. 16 divided by 2 is 8. So that's the value that's going to go in this log base 2 of 8. So that's the first part. We've combined it. We've rewritten it. But now we need to evaluate. What does this actually equal? Again, to figure this out in your head, think of it more in exponential form. So if you think about this problem as an exponential equation, it would be 2 to the x power equals 8. So now look at this. 2 to what power is 8? Well, count in your hand, right? 2 times 2. 2 times 2 is 4. And then if you take 4 times 2, 4 times 2 is 8. So that's 3 2's multiplied together. Therefore, it's 2 to the third power equals 8. So x, or whatever this is equal to 3. Log base 2 of 8 is equal to 3. So that's why you'll see it on the answer sheet that way. Number 13, we've got log 25 plus log 4. Again, just like in number 11, we're going to combine these logs into one log. And since they're both common logs, this will also be a common log. So plus, remember, means multiply. So 25 times 4. 25 times 4 is 100. So we have the log base of 100. Now, what does this equal, though? Part 2, right? We want to know what this is evaluating into. So remember that the base here is 10. So think of this as an exponential equation. It's going to be 10 to the x power is equal to 100. So ask yourself, 10 to what power is 100? Well, it's 10 squared, right? 10 to the second power. So that tells me that this is equal to 2. That's the log of 100 is equal to 2. Number 14. Number 14, we have a log base 3 of 135 minus a log base 3 of 5. Similarly, we're going to combine these two logs into one logarithm with a base 3, but minus means divide. So 135 divided by 5 is 27. So we combine and we get the log base 3 of 27. But now what does this equal? Again, we still don't know. So my trick is to think of this problem as an exponential problem. And if I do that, it'll be 3 to the x power is equal to 27. So now I just got to ask myself, well, 3 to what power is 27? Well, we can write it out if we don't know it already. 3 times 3 makes 9, right? Okay, so we take 9 times 3. 9 times 3 makes 27. So that was 3 multiplied by itself 3 times, so it must be 3 to the third power. So that tells me that this is equal to 3. All right, now to nearly wrap things up, number 15. We're going to determine whether these are growth and decay. So we have f of x equals 5 times 1.2 to the x power. So to determine whether it's growth or decay, we just have to look at these number in parentheses. That's our b value. And if it's bigger than 1, it's growth. If it's smaller than 1, it's decay. So 1.2 is bigger than 1. Therefore, this is growth. All right, but we also want to know what's the rate of growth. So here's what I do. I think about this number as money. So if I see 1.2, I'm thinking, okay, that's basically $1.20, right? So to answer the rate part, you kind of have to think about it as, well, how far away from 1 is it? Is it, we know it's greater than 1, so it's growth, but how much greater than 1, right? Well, $1.20 is, 20 cents more than 1. And 20 cents would be 20%. So it's growth by 20%. Now, if I lost you, stick with me. We'll try number 16 together. Okay, number 16, we have f of x equal to 120 times 0.91 to the x power. So our b value here is 0.91. It's smaller than 1, so that tells us it's decay. But now, think about it again as money, right? This is 91 cents. Okay, but I'm asking, well, how much short of $1 is it? Because again, to determine the rate, it's the difference between this number and 1. So 91 cents compared to $1, this is 9 cents short of $1. So that means we're decaying by 9%. Decay is a little bit trickier, but it makes a lot more sense when you think about it in terms of money. I always think about this kind of stuff in terms of money. It just makes decimals easier to work with in my mind. So hopefully maybe that trick will help you too. Number 17, we have f of x equals 970, 1.08 to the x power. So our b value is bigger than 1, so this is growth. Again, how much more than 1 is it? Well, this is, if that's $1.08, $1.08 is 8 cents more than 1, therefore 8% growth. And finally, number 18, we have f of x equals 7,253 times 0.79 to the x power. 0.79 is smaller than 1, so it's decay. But again, think, if that's 79 cents, how short of $1 are we? 79 cents is 21 cents short of $1. So 21 cents short means 21% decay. So that's it for part 1. I'll definitely cover part 2 in the next video. It's probably going to be a little longer. So I'm sorry in advance for that, but I hope this helps. Let me know if you guys still have any questions. I'll see you in part 2. All right, bye.